So in this video, I'm specifically going to review discriminant function analysis, comparing it as a post hoc analysis, alternative post hoc analysis for a MANOVA as compared to the one-way univariate ANOVAs discussed in this lecture. The purpose of a discriminant function analysis is to predict group membership from a number of continuous variables. So that's going to sound a little bit backwards and kind of bring up some terms that we're used to other things. We're going to do prediction even though we're in the kind of mean comparison or categorical side of the world. And instead of trying to predict a continuous variable, we're going to try to be predicting group membership. So now all of a sudden we're trying to have our outcome variable be categorical in nature. We really haven't seen that at all this semester. In many ways, discriminant function analysis, or DA, is considered the other side of the coin for MANOVA. Both are considered multivariate. Both predict against type 1 error, which are major benefits to using the discriminant function analysis as the post hoc. Both use a lot of very similar statistics. You're going to find some statistics that are presented in MANOVA, some that are presented in discriminant function analysis. They're very similar. You're going to be using, still partially squared, still Wilks lambda, and so on. But they also give some complementary information to kind of create a more complete picture when you pair them together. Not the only major difference, but one of the major differences is that we're trying to switch the independent and dependent variables. So the objective here is to predict group membership using a weighted linear composite. We'll go over what that means in a second, but a weighted linear composite from continuous independent variables. The goal is to describe the nature of differences between those groups. So think back into high school when you had to do a type of career questionnaire where you did, scores on math and English and science and so on, and based on your outcome, it told you might want to look for a career in business, you might want to look for a career in engineering or science or what have you. Basically, what the discriminant function analysis is it's looking at all of these different variables. It's looking at how well you did in math, how well you did in science, how well you did in English, and trying to separate out, based on the strengths and weaknesses, what is the best potential outcome for you. So those formulas that were used to help determine what's that potential outcome were based in discriminant analysis, where previous research identified that people who do well in business have high writing skills, high analytical skills, and so on. This is all based on the creation of a weighted linear composite. By definition, a weighted linear composite is a function where x variables are added and subtracted from one another. Visually, it looks a little bit more familiar as to something like this, where you have this initial weighted linear composite that looks at y equals 0.35x1, 0.20x2, 0.40x3, and 0.05x4. This should look pretty familiar, as this is the weighted linear composite to create your final grade, where 35% of your final grade is based on your homeworks, 20% is based on your forms, 40% is based on your exams, and 5% is based on your annotated bibliography. Variables with higher weightings are going to contribute greater to the final grade, so exams and homeworks, whereas smaller weightings like the annotated bibliography really aren't going to affect your grade a ton. They still play a role, but not a very big one. So in that case, to go back to our example with the career scaling test, somebody who has high English skill or somebody who's going to business, it might be less important for them to have high kind of deductive reasoning, but other analytical skills might be important. So some things will be weighted higher, some things will be weighted lower. We've seen weighted linear composites earlier this semester. We just didn't really call them that. In linear regression, we were attempting to create a single function or a line of best fit that minimized the individual differences, and that's going to be a key point because that's a major difference. Minimize the individual differences of our sample using the least squares principle through a combination of multiple predictors. And ultimately, we got an equation that looks like this y prime equation. Like multiple regression, and I'm going to use MR a lot in the next couple slides, discriminant function analysis attempts to conduct prediction by developing an optimal weighted linear composite. You can do this either standardized or unstandardized, just like regression. Both use sets of continuous variables as predictor variables, so that's pretty much the same. However, in discriminant function analysis, there are varying differences, the first of which is what they are predicting. As we described earlier, multiple regression was trying to look at a single y scores on a y outcome continuous variable. Discriminant function analysis is trying to look for group membership. And we had no groups in regression, so that's a big difference. In regression, we also saw that the functions could be presented as either standardized or unstandardized. That's going to be the same in discriminant function analysis. But when we look at what we mean by the composites, the goal of it is a little bit different. An optimal weighted linear composite. So what is the goal of optimal? How do you get the best regression equation or best function? Well, in multiple regression, the best possible function uses the least squares principle to develop one function to minimize the sum of squares residual or minimize error and maximize the correlation between y and y prime. Basically, what we were trying to do was increase r to be as high as possible. So y to y prime. Look at that correlation. Increase multiple r to be high as possible, and if multiple r is high, then we are also going to then, or that would also suggest that r squared is high. In discriminant function analysis, we're going to make one or more equations that maximize sum of squares between groups. So instead of trying to minimize error, our goal here is to try to maximize differences. Now, instead of just making one single equation, we could make multiple equations to maximize differences. And the way that we determine how many equations we're going to make is based on either the number of groups, so k minus 1, or the number of predictors, p, whichever is smaller. In my example, where I'm looking at the differences between masculine, feminine, undifferentiated, and androgynous, I have 4 groups, so that would lead to 3, and I also have 3 predictors, so I'm going to get 3 equations here. In how do we assess how good this optimal linear composites that we're going to create are? In multiple regression, that was through multiple r, so increase and explain variance, consequently decreasing standard error of the estimate, trying to minimize the size of the confidence interval to increase accuracy. In discriminant function analysis, we're going to use different statistics. Those are going to include eigenvalues, canonical correlations, and percentage of correctly classified cases. So that's some of the material I'll be presenting in the rest of this video. In discriminant analysis, the researcher can develop a function or functions that describes the nature of the differences between groups. So you can see here how what we're trying to do is we see this one visual of all this group sort of being paired together, and we're not so much discriminating between the groups that are, if I make this bigger, we're not discriminating very well between the ones that are stars and the ones that are dark circles and diamonds, but we discriminate pretty well between the circles and those groups with this function. So in discriminant analysis, the researcher develops a function or functions that describes the nature of differences between groups. These functions can be standardized or unstandardized, just like in regression. We have D11x1, D12x2, D1kxk. Here, we see the standardized version uses z-scores. So you can have z-scores in place, as opposed to betas, which was the standardized weighting in regression. The units of a D function don't matter. Typically, they are scaled to a mean of 0 and a variance of 1, but this really doesn't matter what does matter is how well these functions can discriminate between groups. So we don't typically interpret these D units very intensely. Now, different functions might be better at differentiating groups than other functions. Usually, function 1 is the best, where function 1 might best separate group 1 from groups 2 and 3, which is what we saw in that last visual, But then function 2 might be better at separating group 3 from 1 and 2. It really sort of depends on how much explained variance you can pull from your predictor variables. Boundary rules are developed to help make decisions about classifications. Graphically, this is depicted by this territorial map that you see here on the right. I'm going to expand this territorial map. And what you're seeing here is a sort of the development of boundaries based on these scores, where we can see a lot of 1s over here, we can see a lot of sort of 3s over here. The 2s are sort of getting mixed up here, so we're not doing so well with predicting the difference between the 2s and the 1s and the 3s, but we've created boundaries. And you can get a territorial map in SPSS. It's not going to be colored as nicely as this one, but you'd still get similar types of information. So let's continue on. Given the multivariate nature of discriminant analysis, they are often conducted in combination with MANOVA. Both analyses overlap with some information, and both provide their own unique information. Given that one of the objectives of discriminant analysis is to describe the nature of differences between groups, it becomes a logical post hoc to MANOVA, as we discussed before. Given your research question, however, discriminant analysis can also be used by itself. If your goal is to predict group membership from a series of continuous variables, you don't need the MANOVA, just go straight to a discriminant analysis. So we start by using the box M test, just like we used it for the MANOVA, using the same criteria as before. Ideally, you want non-significant difference, apply the appropriate alpha level given the sample size. So I have a fairly decent sample size here, so we probably want alpha here to be smaller. Regardless, I've easily met an alpha greater than 0.05. We're going to get the test of equality of group means. This gets performed, and essentially what this is SPSS is giving you one-way univariate ANOVAs that tell you whether or not mean differences exist across the groups for your variable when not controlling for the intercorrelations. In inferential analysis, where DA is performed, the univariate results can provide a basis of comparison. So this is a helpful statistic. We saw this already earlier in the lecture, where we saw that all three of these things had significant differences amongst our 4 groups. This is just immediately performed as one of the options in MANOVA. You wouldn't typically report these findings because they inflate the type 1 error, just like we described, unless you use a Bonferroni adjustment. If you use a Bonferroni adjustment in this situation, what you've done is you divide alpha by 3, which gets me 0.017. Now I have a more strict analysis. Using the Bonferroni adjustment, only self-esteem would be considered statistically significant. Well, that makes sense if we compare the findings that we saw in the first half of this lecture. Then you are given the correlations that pool the average correlation scores for the predictors across the 4 groups. We want there to be at least one moderate correlation among the variables, but like multiple regression, we don't want high multicollinearity. So if we look at these correlations, 0.34, 0.35, 0.38, we are in the moderate area, but we're not necessarily strong moderate, 0.5, 0.6, 0.7. So you're going to see that we really aren't going to be able to differentiate groups hugely, and that's really because we don't have much information here. We have weak to moderate correlations, not moderate to strong. Now, when you get the data, what you're going to get is still a series of Wilks lambda. Start by reviewing this omnibus statistic, or omnibus to test statistic. Just like MANOVA, Wilks is still a measure of unexplained variance. It's still going to be calculated as the determinant of within over the determinant of total. That's Wilks lambda. Here, Wilks lambda is converted into a chi-square for testing statistical significance instead of F ratio like we saw for MANOVA. If we take a look across our overall things, it's almost easier to read this table backwards. Because what this does is, if I test function 3 alone, what it's telling me is that does not significantly differentiate between the groups. So function 3, not very useful. Now I go up one layer, and this tells me function 2 and 3. And if I go across function 2, it's very high. That's just a lot of unexplained variance, and it's also non-significant. So it's saying when in combination, functions 2 and 3 do not explain differences between my groups very well, or do not predict differences between my groups. So when we get up here, what we're seeing with this statistical significance and that same Wilks lambda of 0.803, what we're seeing is only function 1 really does discriminate between our 4 groups. When you add function 2 and 3, they aren't going to add much explained variance. So really, function 1, that's the only one that's super useful. Function 1 being the only one that's significant is not uncommon. Function 1 is developed by best discriminating among our groups. Function 2, when it's developed by SPSS, cannot correlate to function 1. That's a major restriction, and must discriminate between groups not only not using any of the variance explained by 1, so it has to search out other explained variance. If there isn't more explained variance to use, function 2 is not going to be significant. Then function 3 is going to be harder, because not only can't correlate to either function 1 or function 2, and it used to have to use a whole different set of explained variance. So often, most of the explained variance is found by function 1. Sometimes you get a good function 2. It's really hard to keep going past functions 1 and 2. So the next set of statistics we're going to look at is an eigenvalue. An eigenvalue actually uses lowercase lambda. That's just what you have here. And it's analogous to an F ratio in that it's determined by calculating the determinant of between over the determinant of within. So explained over unexplained, but in a multivariate perspective. As a result, a higher eigenvalue represents greater explained variance. A second statistic that comes in here is the canonical correlation. Canonical correlation is simply a multivariate correlation. It looks at how a set of variables correlate. So a canonical correlation in a DFA is the effect size for each function that represents the correlation of how strongly the discriminant function scores are correlated with group membership. If we square the canonical correlation, we obtain partial eta squared, or the percentage of explained variance that function explains of group membership. So if I look at my canonical correlation up here for function 1, I'm going to now square it down here at the bottom. 0.442 squared is 0.195. That equals 1 minus Wilks, which Wilks for function 1, which is also equal to partial eta squared for function 1. So my function 1 explains approximately 20% of the variance between groups. That formula is also presented up here in the right-hand corner, showing you the relationships here between a canonical correlation, or R sub C, equals the square root of eigenvalue over 1 plus eigenvalue, which also equals the square root of partial eta squared. So after the effect sizes, the next statistics we're going to get are the unstandardized coefficients. SPSS provides unstandard coefficients just like B-weights. However, they don't typically interpret or help in the interpretation of the differences of groups. They can be used to generate discriminant function scores to try to predict group membership based on raw scores, but in terms of the overall interpretation, they're not so useful. They're more useful in application. A standardized coefficient are equivalent to beta from multiple regression. They are used to create a standardized function. So these are the most useful statistics that we're going to get in terms of coefficients. While there is no statistical significance test for contributing variables, what we use is an arbitrary cutoff, typically around 0.50. And it sounds arbitrary, but in some ways it's often called arbitrary, but it doesn't actually seem arbitrary because 0.50 is a decent moderate correlation to determine if your variable has a substantial contribution or weighting. In function 1, self-esteem would be considered the only variable with a substantial amount of weight. If we look across, this one is well above 0.50, where locus of control and neuroticism are very small. The direction and intensity of these correlations may differ in their explanation of group differences when considered the multivariate versus the univariate analysis. So we see positive here, we see negative relationships here, and things sort of change based on the function. The structure matrix allows the researcher to determine the extent to which each variable is correlated to the overall function. Again, we use an overall arbitrary cutoff to make decisions, usually 0.50. Again, we can see self-esteem is the only one that's above there. What this is correlating is, what that means is essentially we see self-esteem has a correlation of 0.9999 to function 1, whereas locus of control and neuroticism both have moderate to weak correlations to function 1. So overall, self-esteem is really the only useful variable in function 1. In function 2, as we look down, although non-significant, we know that function 2 is non-significant, locus of control is the major contributing factor. When we get to function 3, neuroticism is the major contributing factor here. It's the only one. However, what we know is function 2 and function 3 do not substantially contribute to understanding groups of mean differences. So we don't need to interpret those. At this point, we've reviewed a few types of data, and so let's sort of take it all in. With the Bonferroni correction, we know that self-esteem was the only variable that demonstrated a significant difference between groups in a univariate perspective. When we looked at a significant function that should describe group differences was found with a medium effect size. So function 1 was statistically significant, and it had a partial eta squared that 19% medium to strong effect size. When examining the standardized coefficients for function 1, self-esteem was the only one that contributed substantially, and when examining the structure coefficient for function 1, again self-esteem was the only one that had a strong correlation. So what we're seeing here is the output from our DFA is saying we have a significant function, self-esteem is the driving force, which sort of matches up with our univariates where self-esteem was the only way significantly difference between the four groups. So let's keep going. At this point, we know that a high score on D1 or function 1 represents a high score on self-esteem because of the positive significant standardized correlation. So, let me find my pointer. To determine how scores on D1 relate to group membership, we use centroids. A centroid is a mean of a score on each discriminant function for members of one group. For function 1, we see that undifferentiated had a relatively high mean, while androgynous and masculine had relatively low means. Notice that for functions 2, the difference in means are much smaller because it's a lot harder to discriminate between groups. So let's take a look at this again. We see up here, let me even increase the size of this table. Undifferentiated has a much higher correlation here, or much higher mean here, and then overall we can't really discriminate between these two means. They're pretty close, but across the groups we have a higher mean there. Functions 2 and function 3, see how everything is really, really small? You can't really separate them. So here, really low, androgynous is the smallest, followed by masculine, followed by feminine, followed by undifferentiated. So we can see 4 clearly different means. Functions 2, we really can't see much difference in the mean. In functions 3, it's also really hard to see the means. Not surprisingly, functions 2 and 3 were statistically non-significant. That territorial map that I showed you earlier can sometimes be helpful to visualize all this information that I'm providing. However, visually, real data isn't as pretty as one might like, or as nice as that visual I showed you. So I'm going to show you 2 visuals, the actual territorial map, and then an SPSS rendition that demonstrates the data a little differently. So this is the territorial map, and these where we have over here we can see that 1s are identified as undifferentiated, feminine is identified as 2s, 3s are masculines, 4s are androgynous. So we can see androgynous are a lot over here. 4s, we can see a lot of 2s over here in the middle. So feminine being between androgynous and undifferentiated. We have undifferentiated over here. We don't actually see any 4s. There's no masculine, 3s. There's no masculine anywhere on here. And visually, what these little asterisks mean, we have to get this bigger, it's hard to see them, and I put them in red for a reason. These individual asterisks are actually those centroids. So over here, this first asterisk is the centroid for androgynous. Then we have the centroid for feminine, masculine, and undifferentiated is farthest to the right. So you can see we're really not pushing those centroids very far apart. Let me see if I can show you another visual where what I've done was I put the scores for the function 1 down the x-axis, and I used function 2 just to create a bivariate map. Now, undifferentiated is my blue group, and we can see most of them are sort of bulking up here. Androgynous is my purple group. Most of them are sort of down here. And then I plotted my centroids, and we can see this purple centroid, again, I'm going to enlarge. The purple centroid is farthest here to the left, that's androgynous. Then my orange centroid is masculine, the next one. Then I have my green centroid in this asterisk over here, that's feminine, but we can see how the green dots are sort of scattered all throughout here. And then this last centroid, blue, is undifferentiated. So we can see that we're really kind of breaking between the blue and the purple, or the undifferentiated and the androgynous, but not really doing much for feminine and masculine. This last table tells us how well our function, or a combination of functions, predicted group membership. Overall, I was able to predict 51.9% correctly, and again, I'll enlarge this, but you can see that number down at the bottom here. That serves as a measure of meaningful significance. It tells me how good my function did, similar to an R-squared type value. So that's a pretty useful number. But if we look down this diagonal, what this is doing is it's telling me how many participants, or what percentage of my participants, I correctly classified. And that answer is down the diagonal. So of the original undifferentiated participants, 7% were correctly classified. Of the feminine participants, 86% were correctly classified. Of the masculine participants, none were correctly classified, but I didn't actually have any to begin with, which is probably should have came out in data screening. Androgynous, 42% were correctly classified. Overall, just over 50%, which is not all that great because it's essentially a flip of the coin. Overall, feminine were the most correctly classified, but they were also essentially down the middle. Masculine were not correctly classified at all, but we had no information to go off of. So overall, self-esteem was the most useful predictor. It helped drive the differences between undifferentiated and androgynous. High self-esteem scores were predictive of undifferentiated, but overall the percentage of classification was low. The highest correct classification was moderate scores of feminine, and masculine was not predicted at all. Those would be the takeaway points that I would write up in my results and discussion. As a quick comparison to those univariates that were earlier in the lecture, consider how our findings compared. Undifferentiated had higher self-esteem than all other groups. We saw that in the univariates. Feminine individuals had higher self-esteem than androgynous and masculine. We sort of saw that they fell in the middle and were closer to undifferentiated than they were to androgynous. Undifferentiated individuals had higher locus of control and neuroticism than androgynous differences, but no other significant differences existed. Well, we didn't have it. In our DFA, we couldn't discriminate between using neuroticism or really using neuroticism or locus of control at all. So how is this all that different? Consider that consider at times the differences between MANOVA and DFA and univariate ANOVAs will be much more different. When the intercorrelations of the variables are moderate to high, you would see the multivariate approach actually be able to report that and report greater differences than the univariate approach. But I had relatively moderate to weak correlations amongst my variables. They were all around 0.3, between 0.3 and 0.4. So that would be one of the reasons that perhaps my discriminant analysis didn't work as well as yours might in the future.